That's 17. Okay. Get to. Oh. All right, there we go. So now the fan kicked down, so maybe there was something going on with it. So we're in this section now. Let me make sure my pen works. So far it does. I think what I'll do is, since this section basically has a couple of components to it, I think what I'll do is go to the homework, see what particular problems this has in it. That's right. Things seem to be slow. Wait. Maybe all of a sudden, as soon as I have access. Wait. I tell you what, let's try this. And I'll hit it again. I don't know what happened there. Okay. So we got two more assignments that's going to pop open. I'm not exactly sure where this exists, but that's in 16. So that's 7, so it has to be 8. Doesn't have to be. That's 16. It's got to be 9. Well, I didn't put that many in here again. I need to put more problems in there. Okay. So maybe I'll just take a look at these 4 in no particular order. But I have this at all. Okay, it's got this weird standard. Oh, I'm trying to, oh, okay. It's just haven't taken time to come up. Well, this is a pretty good one. Um, Let me just give you an idea. He has it with a frictionless table, but I'm gonna go ahead and add friction to it, and then just sort of work it that way. And take it part E, part A, B, C, D, and E. But where is okay, there's part A. Usually, okay, given that A2 is the magnitude of the horizontal exertion, what is tension? Oh, he wants it as a term like that. So, here. Let's take a snippet of this thing. Move over to here. Add a new page. And so if you look at this thing, you actually have two blocks. I think I could manage to do it all for the squares. You got that one. And I'll drop it right there. And you got this one. And just drop it right there. If you look at this one, for example, okay, now, where's my pen? Maybe I'll do that. So if you look at just that one, okay. Oh, that was interesting. Look at just that one. Okay. You got a tension in the rope, and you got a, technically, you got an M1G here, and that's all you have. Then you've got to decide what direction is positive or negative. I'm going to purposely complicate the thing by making it positive this way. And you'll see why I'm purposely complicating the thing in a minute. So, some of the forces, and since actually, I mean, I guess I could call that y is equal to mass times acceleration of y, but I'm just going to say it's implied that this is the direction I'm doing it in. Remove those subscripts. And if you look at this being positive, which matches that, you'll see a T, because it's going in that direction, minus an M1G is equal to, and this is M1 times acceleration. And I'll go ahead and call it 1, because there'll be accelerations of both blocks. And you're kind of done right now. Now, if he would have given you the M1, you could put that number in, this number, the G, but for right now, you're sort of done there. And then if you kind of come over to this one, since, and I don't know if he implied this or not, but these two pulleys have no mass. So you essentially have this, where you have this tension being the same because there's no mass. If there was a mass of this pulley, the tension in this line would be different than that one. It would be different than that one. unless they were not moving. If they were not moving, they would be the same. But you'll have this, which is M2G. If you had friction, now of course you're going to have also a normal force, which the sum of the forces in this direction is getting equal to mass times acceleration in that direction, which is going to be zero because the block's not flying off or landing on the plane. And so what you get is, out of that, N is equal to M2G, and that's pretty much useless unless you had some form of friction here. So if you had some form of friction equals to, or, well, I'll say this, mu times N, which I could just replace it with that, but he said it's no friction. However, if there was a friction, I'll go ahead and write this as if there was, and then I'll get rid of the term. Sum of the forces, I'll go ahead and stay in the x direction. I'll make this positive, equals to mass 2, acceleration 2. And what you see is two of these that are going to the left. And if you had friction, you'd see that. And that's given, well, okay, to be plus mu times N is equal to M2 A2. And essentially you're stuck with that. However, this problem doesn't have that, so that's 0. And so what you get is minus 2t equals M2 A2. And then technically, I guess I should have boxed that one. And so you've got this equation and that equation. The problem is, now it's A1 proportional to A2. And since it's pulleyed and they're tied this way, the most convenient thing to do is drop a coordinate system, head out here and call this SA2, and have this one come down here and say S1. And then the length of the rope is equal to all these little sections here. These sections, which I'll just call a delta, plus this and this, which is 2S2, plus this distance, which is S1. Now, usually I take one derivative, but now I'm going to take two derivatives. If you take two derivatives, that thing is 0, that thing is 0, so what you get is 0 is equal to 2S2 double dot plus S1 double dot, where the double dot is the same thing as, so like, or here, I'll just do it one more time. But I'm going to use this one. 2 plus this. So there you go with that. So the thing is, I purposely confuse things by making, okay, up here, this is positive, and down here, so I'm making these two vectors go opposite directions. Whereas here, this goes to the right, and so does that. So this means if I'm basically going to do this, now, move the whole thing to the right and maybe down a little bit. Get the escape and that. So if I'm relating these two, I would say S1 double dot is actually in the opposite direction of the acceleration. And that's because of these two, my purposeful making them go in opposite direction. And the reason I was purposely doing that is to show that this can happen. In this particular case, you're stuck with a datum, and so ordinarily, and he's done it right here where he's done an X and a Y. And so ordinarily you make this positive and that positive. But this part right here makes the movement down positive as far as S is concerned. So hold on to that for a second. And then look at this relationship. And what you'll find is S2 double dot is equal to acceleration 2. Because this one's going to the right and so is that one. And so since they're both going in the same direction, they're basically equal to each other and not the negative of each other. So now I have this equation tied with this one and tied with that one. And so what I'm going to do is repeat those down here. So what I've got, let's see, I've got a space that's kind of right down here. I'll work on this. So this is what I'm working on right now. So I've got the first equation which came out, which is 2 S2 double dot plus S1 double dot, which that equation came from right there. And then I've got minus S1 double dot equals to A1, and that equation came from right there. And then I got the one that came from up here is S2 double dot is equal to A2. So now what I can do is stick this one in here, stick that one in there, and what I'll get is 0 is equal to, okay, let me get rid of these little vectors right here. 2, instead of S2, I'm going to grab A2. And then instead of S1 going here, I'm going to get a minus A1. And so, if we move one of them over, I don't know which one. A1 is equal to 2A2. Likewise, you would see that B1 is equal to B2. Now, does that make sense if, wait a minute. Okay, if I'm going to make it make sense, I'm going to get the picture again and just move it down. There's too many things going on. So, what I have done, okay, so I'm in the A1 and A2 world, which means I'm now in this one. Here, just to make sure. I'm in this one. And I'm in this one. So up and to the right. So up and to the right. So if this is 1 right here, if this is moving at, I'm just saying 1 foot per second, then this is telling me this is moving at 2 feet per second. And so that makes sense. What wouldn't make sense is if I had this one going this way, because that would look weird. That would probably not even be possible. So I think, or not only wouldn't be possible, if the rope has a tension in it, it wouldn't be possible. So now I've got, okay, let's see if I can just copy them. Maybe like this. And I'm just copying again. Oops. Okay. Even that one. And then go ahead and make it. Do that one. And so now I've got three equations that I can work off of. If, for example, I don't remember which one he was interested in first, but it really doesn't matter. Where did the that it? Where's that is? And that's okay. You know, express the tension in the terms of M2 and A2. Hang on. We want to know the tension as a function of M2 and A2, which means I really need to remove the one out of there. So it depends on how you want to look at this. I don't want to see an A1. So if I don't want to see an A1, I'm going to take this, put this in there. And then, you know what? Let me do this. It's too much space. Makes it hard to. Okay. So if I want to get rid of A1, I can do so by doing that into there. T minus M1 G equals to, you get rid of the A1. Now I'm not sure you can completely get rid of the other term. Express tension in terms of M2 and A2. We'll see if it's possible to remove all of that. So you got tension. Do what now? Oh, that's, yeah, I guess we can. That's making it too easy then. It can't be that easy. I guess so. You know what? We had no friction. That's really sad. Okay. I was going to kind of break them down all the way. Well, okay. Yes, you're correct. Acceleration of the suspended block. Okay, now he's got to have, well, given T, the tension in the string, which I'm assuming was back there, A1, magnitude of vertical. Express the acceleration, magnitude A1. You know. Now, okay, now that's going to be, so A1 is just equal to T minus M1G over M1, or if you wanted to, I don't know whether, you know, I don't know what he's going to come up with. M1, G, and T. M1, G, and T. There you go. Relative acceleration. Given the magnitude of A1, the acceleration. Oh, okay. So this is the third equation. So that's that one. Does he combine them at all? Okay. Using the result from C in equation 4T. Okay. Now he's combining. So part D is combining. Uh-oh. What happened? What? Anyway, I don't know what happened there. What is going on here? Here. Print view. What does print view look like? Nothing. Okay. Oh, I guess this is a situation where you can't fill out You did not open hints for this part. You do not open hints. I didn't know there was hints available. Okay, reducing part from C in equation. There's T as a function A1. Okay. All right, so part E is the last one, in which A1 in terms of M1, M2, and G. So there's no T in there. So I've seen this done a couple of ways. And you know what? I get rid of all this other stuff. And then I'm going to stick this in here or in there. So say T minus M1G equals 2. This time I'm going to stick the A1. So actually, I guess I misspoke. I'm going to stick it in there. 2M1A2. And then minus 2T equals 2M2A2. Then if I just multiply the top by 2, 2, and 4, and then add them, we get nothing. 2M1G equals to, I don't know, M2 plus 4M1 and A2. But then let me relook. A1 in terms of, they wanted A1. Am I getting A1? No, I'm getting A2. So I should have done this. Should have taken this one and shoved it into that one. So it's on me here, M1, A1, and then take this one and A2 would be half M2, A1. That would make this different. Wouldn't affect anything over there. But then I got to multiply the whole thing by 2. So I don't know which one's the M1 plus M2 over 2, A1. And then I can just say A1. It's just a fact of reducing things now. I don't know what's the best way. 2 M1G over 2 M1 plus M2 over 2. How is it reduced? That's a good question. I don't know. But that's A as a function of M1, M2, and G. And M1, M2, and G. So that's, okay. Oh, there we go. A1 in terms of M1, M2, and G. I'm going to look at the solution view that last and see what he would like. That's weird. He's got, it disappeared. Okay. He gets rid of the 2's and leaves it as a 4. That's all he's doing. So, what he's doing, and basically get M1G. Let's still cancel that one out, and then you'll get another one. And that's it. So that's all he's doing. Let's see. 1, 2. Thing doesn't move very fast, and then it gets stuck. So it's like, this one, hang on, some time. Okay, this one's a similar one. Oh, this one has numbers, so that's a little bit better. He's got 3 of things in there. Should be probably acceleration 1, acceleration 2, and then, oh, he's doing a distance too. So he's doing slightly different, but the process is exactly the same. Okay. So this time, what I'll do is I'll do the same thing, although I'll do the mode being slightly different. So there's the first one. And what I'll do is drop that over here. And then the second one. The second one, what I'm going to do, I'm going to include that. And then drop that one down here. Okay, so all you're doing here is the same process. I shouldn't have copied that one part, but it's okay. So you're going to have a tension here. You're going to have normal force here. If you have friction, you're going to have some frictional force here. Let me see if he does have friction. It would be beneficial to read the problem. Yes, we got friction. So I'm pretty sure if we do this, like, in other words, if we had a problem that looked like this, you would release the weight. This weight would go down and pull this one this way. However, it is possible that this weight is so light that this is the direction. So what we've got to do is assume a direction, or we can find out its direction. So what I'm going to do is I'm going to attempt to find out its direction first. So if you'll bear with me, I'll do this in two sections. One, the first phase of the problem will be finding out the direction. So I'm going to put these together. Let's see. So this phase 1 will be finding the direction. So this is going to be the part that we're going to do the finding of the direction. So when we find the direction, what we're going to do is somebody is going to reach in here and hold their hand on this somehow. Okay, so in other words, if it's not in motion, somebody goes in here and we'll pick this block, for example. So before it gets in motion, somebody is either going to hold this block this way. They're going to hold this block from moving by putting a force on it this way, or they're going to put a force on the block this way, and they're going to keep it from moving. So there's no friction yet. You're just keeping the thing from moving. And so you're basically going to be putting some sort of force. So let's assume there's no friction yet. Nothing's happening. We want to know, does this thing slide this way or does it actually go that way? So what we're going to do is I'm just going to put a tension here and a tension here because they're all the same. It's not moving yet. There's no movement here. So I think, yeah, let me get rid of this. Okay. Okay. So there's nothing moving yet. So if there's nothing moving over here, there's no movement, then sum of the forces equals 0. And that means 2t is equal to, and the free body diagram looks like this. So again, there's no movement yet. Okay. M1 times G. If there's no movement, that means this is the case, and we can just do this. Now, hang on. You got a component this way. You got a component this way. Now, this component this way is going to be 5/13 of this value, which is M2G, and therefore, let's also put a force on it. I'm going to say, I'm going to hold it with this force here. So I'm holding this force. So if you sum forces in this way, being positive along here, and it's equal to 0 because it's not moving yet, the first thing you'll see is minus F from this force minus 5/13 of M2G, and then this force, which actually is, I'll go ahead and say plus T, but we know T is 1/2 of M1G. So I can just replace that, 1/2 of M1G. Now my question is F positive or negative? So I'm going to move F over, and I'm going to go ahead and say 1/2 M1G minus 5/13. And I'm doing this because this is a situation that always works. I don't know these values. Okay, so M1 is 38. Okay, let me go through. M1 is equal to 38. M2 is equal to 15. And that's all I really need to know. So is it positive or negative? 1/2. I really don't even care what G is because I can just leave it in as G. I just want to know if F is positive, meaning I'm actually holding this thing and holding this weight from sliding in that direction. If it's negative, it means it's going to go the other direction. So M1, which is 38, G minus 5/13, 15G. Okay, so I don't know anything else to do, but it doesn't matter what G is, so I'm going to take it out. And I'm going to calculate this using a funny, doesn't matter what the value is, it just matters what the sum is. Looks like it's a positive 172/13, or doesn't matter what that number is, it just matters that it's positive. So because it's positive, that means this is true, and I'm having to hold this mass from moving in that direction. The reason I wanted to know that is because of this. If I take a look at this, let's do it right here. Take a look at this block, and it is moving in this direction. The friction force moves opposite direction. If it's moving this direction, the friction force is the other direction. So I've got to know which direction it moves. So it turns out it's moving like this. And so its friction force, I'm trying to avoid, here I'll just do it like this. Friction force is like that. Now that I've got that, what I'm going to do is copy this, move it to the right, and then go back at it the way it should be done with acceleration. And then I guess I can pick this up next time. Let's see. There's my, I better use this. So this part of the problem is seeking to answer the question of, I'll just copy it, put it over, and I'll say this was done to figure out which way which way was it moving? And we answered the thing by figuring out it's moving that way, which means this thing is moving that way. So now that I have that, I can go back, since I already have my free body diagram, I can go back here and sort of take this off, take this off, take that off. I can work on the right, and on the right, I'll assume that this, I'll assume this direction is positive, because now I know it's going to go falling down, and I'll say M1 times acceleration. Now it turns out I have 2t minus 2t, in the other direction, 2 positive there, plus this is equal to M1A1. So I got an equation set right here. Then you got to come back over here, and I really monkeyed this one up, but let's take this off, take this off. There's no more force here, but what I've got is M to A2, and I'm going to go ahead and make that positive, which is what I did here, equal to. If that's positive, I get a T sitting right there. I still get this minus 5/13. It's essentially this component right there. And I get this component, which is just mu times normal. I hadn't figured out the normal yet. And that is going in the slowing down direction, mu times normal, which I'll have to find that in a second. So now all this is kind of for naught. This was just to figure out. Now that's not, that is, those are the actual values. So I'm going to just sort of keep those over in the middle somewhere. And maybe just box them. So I'll remember to go looking for them. Okay. So now I've got, okay, do I have everything? I do, but I don't have the normal yet. So what I've got to do is sum the forces in this direction vertically. And what I've got there, it's not accelerating onto or off of the board or the place there. So what I've got is a normal, which is this one. And that's going to just say the normal is equal to 12/13 of M to G. Because this is not really done very well in the sense that, here, I'll move it out of the way. This really belongs with this component, and this component is 12/13 of M2G. So those are those two. Now that I've got that, I'm going to put this in here. And what I'll do is M to A2 T minus 5/13 M2G minus mu, this kind of weird, 12/13. I'm taking this, 12/13 M2G. Okay, now I can, well, I say I can yet, but I can't yet. And that is, I can't go in and solve these because I do not have the relationship between the motions at 1 and 2, except that I can find that pretty easily. This is the S1, this is the S2. We'll get close to the end, so maybe we'll just freeze it here and just wrap it up next time. So we'll just call it good. I should have brought some caffeine.